Hello! In this video, we are going to prove the following theorem. Let A and B be sets. If A is finite and B is a subset of A, then B is finite, and the number of elements in B is less than or equal to the number of elements in A. Second, if B is not equal to A, then the number of elements in B is strictly less than the number of elements in A. Now, before we get into the proof, let's get some context. First of all, what do we mean by finite? Well, to state what we mean by this, first, I would like to say that given any two sets A and B, we will write this to mean the same thing as saying there exists a bijection from this set to this set. Now, for our purposes, we're going to say that the natural numbers includes 0. And we're going to say that for each natural number n, we define the following set. We define the set In to be the set of all positive integers less than or equal to n, where the positive integers are really just the natural numbers not including 0. Okay, now let's talk about what we mean by finite. Well, given any set A, we will say that A is finite if there exists a natural number n, such that there is a bijection from In to A. But it turns out that this natural number n, which satisfies this condition, is the only natural number which satisfies this condition. So it turns out it's actually unique, which we've proved in a previous video. And we denote this unique natural number n as the number of elements in A. And we denote it in the following way. Just like this. So that's what we mean by finite set. So now let's get into the proof. And before we actually prove what we're trying to prove here, we're actually going to prove a lemma, which looks really similar to this. We're going to prove for all natural numbers n, we have that for all subsets A of In, the following two are true. The first is that A is finite, and the number of elements in A is less than or equal to n. The second is, if A is not equal to In, then the number of elements in A is strictly less than n. And to prove this, we're going to primarily rely on 3 facts regarding finite sets. The first is that given any set A, the number of elements in A is equal to 0 if and only if A is empty. The second is that given any set A, the number of elements in A is equal to 1 if and only if A is a singleton set. And the third is given any two sets A and B, which are finite and disjoint, well, the union of A and B is also finite. Moreover, the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B. Okay, so now let's get into proving this statement. And since we're trying to prove a statement about all natural numbers, let's use mathematical induction. And to do so, let's start with the base case. And in the base case, we're trying to prove that this is true in the case where n is equal to 0. Which means we're trying to prove that for all subsets A of I0, we have that A is finite and the number of elements in A is less than or equal to 0. And second, if A is not equal to I0, then the number of elements in A is strictly less than 0. So this is what we're trying to prove. Since we're trying to prove a statement about every subset of I0, give me an arbitrary subset of I0. I'll call it A. Our whole goal from here is to prove that both 1 and 2 are true. And to start, well, what is I0? I0 is precisely this set where we replace n with 0. So really, I0 is the set of all positive integers less than or equal to 0. But wait a minute, there are no positive integers less than or equal to 0. So I0 is empty. So we can replace I0 here with the empty set. And then, since A is a subset of the empty set, it follows that A must be the empty set as well. And by our first fact, since A is empty, it follows that A is finite and the number of elements in A is equal to 0. So what we have here is that A is finite and the number of elements in A is less than or equal to 0. So 1 holds. And next, we know that A is equal to the empty set, which is equal to I0. So we see that A is equal to I0, which means the hypothesis of 2 is false. Therefore, 2 is vacuously true. So we have proven that both 1 and 2 are true. And since A was an arbitrary subset of I0, this means for all subsets A of I0, 1 and 2 is true. So this completes the base case. Now let's move on to the induction step. Now in the induction step, we give ourselves an arbitrary natural number where this is true. The whole goal of the induction step is to show that this is also true for n plus 1. So really, what we're trying to prove here is this. So for all subsets A of in plus 1, both 1 and 2 are true, where we replace n with n plus 1. So we're trying to prove a statement about every subset of in plus 1, so give me an arbitrary subset of in plus 1. I'll call it A. Our whole goal from here is to prove that 1 and 2 are true. And to do so, we're going to divide this up into 3 cases. Either A is equal to in plus 1, or A is not equal to in plus 1 and n plus 1 is not an element of A, or A is not equal to in plus 1 and n plus 1 is an element of A. Let's start with the first case where A is equal to in plus 1. Now, if you recall, given any set A, there exists a bijection from A to itself. So, since A is equal to in plus 1, we can take the first A here and replace it with in plus 1. So what do we have now? Well, we see that this tells us that A satisfies the requirement to be a finite set, because there exists a natural number that satisfies this condition, namely n plus 1. And we know that n plus 1 uniquely satisfies this condition. So we denote it in this way and say that the number of elements in A is equal to n plus 1. So what we see here is that A is finite and the number of elements in A is less than or equal to n plus 1. So 1 holds. And also, since A is equal to in plus 1, we see that the hypothesis of 2 is false. So 2 is vacuously true. So we've proven that 1 and 2 are true in the case where A is equal to in plus 1. So this completes our first case. Now let's move on to the second case where A is not equal to in plus 1 and n plus 1 is not an element of A. So why are we considering the possibilities of either n plus 1 is not an element of A versus n plus 1 is an element of A? Well, in this case, we see that A is a subset of in. The reason why is because, well, we know that A is a subset of in plus 1. However, n plus 1 is not an element of A. So we also know that A is a subset of in plus 1 set minus the singleton set of n plus 1. And in plus 1 set minus n plus 1 is equal to in. So really, we say that A is a subset of IN. So we can apply our induction hypothesis, right? We know that for all subsets of IN, that both this and this are true. So since A is a subset of IN, we have that A is finite, and the number of elements in A is less than or equal to N. And we know that N is strictly less than N plus 1. So now what we see here is that A is finite, and the number of elements in A is less than or equal to N plus 1. So part 1 is satisfied, and also, since the number of elements in A is strictly less than N plus 1, we have that the conclusion of 2 is true. So 2 is true. So we have proven that both 1 and 2 hold in our second case. So this completes case 2. Now we're going to move on to case 3, where A is not equal to IN plus 1, and N plus 1 is an element of A. So now let's consider the case where A is not equal to IN plus 1, and N plus 1 is an element of A. Now, this case is probably going to be a little bit trickier than the first two cases, because, well, we can't apply our induction hypothesis to A, because A is not a subset of IN. But we can apply our induction hypothesis to A set minus the singleton set of N plus 1. Because we know that A set minus N plus 1 is a subset of IN plus 1 set minus N plus 1. The reason why is because if we consider an arbitrary element of this set, call it X, well then we see that X is an element of A. And since A is a subset of IN plus 1, it follows that X is an element of IN plus 1. But X is not equal to N plus 1, so X is not equal to N plus 1. Therefore, X is an element of this set. So yeah, this set is definitely a subset of this set. And we know that this set is equal to IN. So A set minus N plus 1 is a subset of IN. So we could apply our induction hypothesis to A set minus N plus 1. However, we could further show that A set minus N plus 1 is not equal to IN. And to see how, well, since A is not equal to IN plus 1, but A is a subset of IN plus 1, this means we must have that IN plus 1 is not a subset of A. What does this mean? Well, it means that there is some element in IN plus 1 that is not in A. I'll call that element T. And since T is not an element of A, and N plus 1 is an element of A, we must have that T is not equal to N plus 1. From here, we see that T is an element of IN plus 1, but not equal to N plus 1. So, T is an element of IN plus 1 set minus N plus 1. And we know that this set is equal to IN. So T is an element of IN. And also, since T is not an element of A, surely it follows that T is not an element of A set minus N plus 1. So, from the fact that T is not an element of A set minus N plus 1, and T is an element of IN, we have that A set minus N plus 1 is not equal to IN. Right? Because they don't share exactly the same elements. Namely, one of them has T, one of them doesn't. So, we see that A set minus N plus 1 is a subset of IN, but not equal to IN. So, we can apply our induction hypothesis to A set minus N plus 1. And we obtain that A set minus N plus 1 is finite, and since A set minus N plus 1 is not equal to IN, it follows that the number of elements in A set minus N plus 1 is strictly less than N. Also, let's note by our second fact that the singleton set of N plus 1 is finite, and the number of elements in it is equal to 1. Now let's apply fact number 3. We see that a set minus n plus 1 and n plus 1 are both finite. But these two sets are also disjoint. By fact number 3, it follows that the union of a set minus n plus 1 and n plus 1 is also finite. And we know that the number of elements is going to be split up like this. So really, the number of elements in the union of these two sets is equal to the number of elements in a set minus n plus 1 plus the number of elements in n plus 1. And let's note that since the number of elements in this set is strictly less than n, if we add this on both sides of the inequality, we get that this is strictly less than n plus 1. Right, now we know that the union of these two sets is equal to the set A, so we can take that set right here and replace it with A. So we see that A is finite, and the number of elements in A is strictly less than n plus 1. So what do we see here? Well, A is finite, and the number of elements in A is less than or equal to n plus 1, so 1 holds. But moreover, the number of elements in A is strictly less than n plus 1, so the conclusion of 2 holds. Therefore, statement 2 must hold. So we have proven that both 1 and 2 are true. So this completes case 3. And this covers every possible case. So we have proven, given A is a subset of n plus 1, well, 1 and 2 are true. So this completes the induction step. And so this closes the induction. So we have proven for all natural numbers n, this is true. So now we're ready to prove the main result. Now, there's another fact regarding finite sets that we're going to use in proving the main result. Given any two sets C and D, if D is finite and there's a bijection from C to D, then C is also finite, and the number of elements in C is equal to the number of elements in D. And we're also going to use another fact, and this one is regarding functions. So let's suppose we have a function f from a to b, and c is a subset of a. Well, we have a function which is called the restriction of f to c, which is a function from c to b, where for every element x in the domain C, the restriction of f to c evaluated at x is equal to f evaluated at x. Right, so f and the restriction of f to c do essentially the same thing. The only difference is we're restricting the domain of f to the domain C. Right, that's the idea. Now, a fact regarding the restrictions of functions is that if f is injective, then the restriction of f to c is also injective. Okay, so now let's get into proving the main result. To start, let's give ourselves two sets A and B, where A is finite and B is a subset of A. Our whole goal is to prove that both 1 and 2 are true. Now, to do so, we're going to consider two cases. Either B is equal to A, or B is not equal to A. So let's first suppose that B is equal to A. Now, in the case where B is equal to A, well, since A is finite, we can just take A and substitute it for B. So B is finite. And since B and A are finite, we know that they are assigned to unique natural numbers, which we call the number of elements in B and the number of elements in A. Well, since B is equal to A, we can substitute one for the other, and we obtain that the number of elements in B is equal to the number of elements in A. So what do we see here? Well, B is finite, and the number of elements in B is less than or equal to the number of elements in A. So 1 holds, and since B is equal to A, this means that the hypothesis of 2 is false. So 2 is vacuously true. So we have proven that both 1 and 2 are true in the case where B is equal to A. So now let's consider the case where B is not equal to A. Now to start, for convenience, since A is finite, let's say that the number of elements in A is equal to n. Right, we know from finite sets, this is the same thing as saying that n is the unique natural number such that we have a bijection from In to A. And also, it turns out if you're given any two sets A and B, if there's a bijection from A to B, then there's a bijection from B to A. So we can actually just swap these two around. So there's a bijection from A to In. And I'll call that bijection F. Now, notice we have a function from A to In, and B is a subset of A. So from what we have written here, we can consider the restriction of F to B. Because F is bijective, we know that F is injective. And from our second fact, we know that since F is injective, we have that the restriction of F to B is also injective. But is the restriction of F to B surjective? Well, it's a good thing that every function is surjective to its range. So the restriction of F to B is surjective to its range. And for convenience, I'll call the range J. Okay, so then what does this tell us? Well, if we treat the restriction of F to B as a function from B to J, then yeah, the restriction of F to B is a bijection from B to J. Because we know that the restriction of F to B is injective, but it's also surjective to J. And so there exists a bijection from B to J. Okay, so then what's the point in all of this? Well, since J is the range of the restriction of F to B, and In is the range of F, we expect the range of the restriction of F to B to be a subset of the range of F. So we expect J to be a subset of In. But because we're working under the condition that B is not equal to A, we also expect J to not be equal to In. If we can show these two things, then it follows from the first fact that we proved that J is finite, and the number of elements in J is strictly less than n. But since there's a bijection from B to J, it follows from this fact that B is also finite, and the number of elements in B is equal to the number of elements in J, which is less than n, which is equal to the number of elements in A. So we will obtain this. And so that's where this is going. So let's first prove these two things. Let's start by proving that J is a subset of In. So we're trying to show that everything in J is also an In, so give me an arbitrary element of J. I'll call it Y. What does it mean for Y to be an element of J? Well, J is equal to the range of the restriction of F to B. So Y is an element of the range of the restriction of F to B. What does it mean to be an element of the range of the restriction of F to B? Well, it means that there is some element in the domain of the restriction of F to B, I'll call it X, such that the restriction of F to B evaluated at X is equal to Y. And this is the same thing as saying X comma Y is an element of the restriction of F to B. But by definition of the restriction of F to B, we know that the restriction of F to B is a subset of F. And since F is a function from A to In, we know that F is a subset of the Cartesian product A times In. So we have an ordered pair that is an element of a Cartesian product. When that happens, if you recall, all that means is that the first coordinate is an element of the first set, and the second coordinate is an element of the second set. So really, Y is an element of In. So, putting this together, we started with an arbitrary element y and j, and deduced that y must then be an element of In. Since y was arbitrary, this means everything in j is also an In. So we have proven that j is a subset of In. But now we want to show that j is not equal to In. And to see how we can do that, let's first move back up to the top. And before we move back to the top, let's write some things down for safekeeping. Now, to see that j is not equal to In, let's use the fact that we're working under the case where b is not equal to a. Since b is not equal to a, but b is a subset of a, this means that a is not a subset of b. So, this means that there is some element in a that is not in b. I'll call that element p. And since p is an element of a, and f is a function from a to In, we know that f has a functional value at p, so I'll call that functional value k. We know that all output values of the function f are elements of In, so f of p is an element of In. So k is an element of In. Well, our claim is that k is not an element of j. So let's assume for a contradiction that k is an element of j. Well, since j is equal to the range of the restriction of f to b, k is an element of the range of f restricted to b. What does this mean? Well, it means that there is some element, say q, in the domain of f restricted to b, such that the restriction of f to b evaluated at q is equal to k. But now, we see that f of p is equal to k, which is equal to f restricted to b evaluated at q, and by the property of restrictions that we have here, we know that f restricted to b evaluated at q is equal to f evaluated at q. So we see that f of p is equal to f of q. So since f is injective, it follows that p is equal to q. And then, since q is an element of b, and p is equal to q, it follows that p is an element of b. So we have that p is an element of b, but this contradicts the fact that p is not an element of b. So we reach a contradiction. So our assumption that k is an element of j leads to a contradiction. So we must instead have that k is not an element of j. So what we see here is that k is not an element of j, and k is an element of In. So we see that j and In don't share exactly the same elements, so they're not equal. So we have that j is a subset of In, but not equal to In. So we can apply this fact to j, right? We will obtain that j is finite, and since j is not equal to In, the number of elements in j is strictly less than n. So notice we have that j is finite, and there's a bijection from b to j. Well, from this fact, it follows that b is finite, and the number of elements in b is equal to the number of elements in j. And the number of elements in j is less than n, and let's recall that we denoted the number of elements in a as n. So this is equal to the number of elements in a. So the number of elements in b is strictly less than the number of elements in a. So what we have here is that b is finite, and the number of elements in b is less than or equal to the number of elements in a. So 1 holds, but also the number of elements in b is strictly less than the number of elements in a. So the conclusion of 2 is true, which means 2 is true. So in the case where b is not equal to a, we have proven that both 1 and 2 are true. So in summary, we considered 2 cases. Either b is equal to a or b is not equal to a. Whichever one of those happens to be the case, 1 and 2 are both true. And that's exactly what we wanted to prove. So given a finite set A and B is a subset of A, 1 and 2 are true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.